So let's just start with reminding you the statement of the principle of inclusion-exclusion, which says the following. If we have a collection of finite sets, A2, A1, A2, AN, which are subsets of another finite set called A, then if we want to determine the cardinality of the set A minus the union of all the sets A1, A2 up to AN, this will have a concise form as a summation over all sets of indices J in the set of indices 1 up to N of -1 to the cardinality of J times the cardinality of AJ, where AJ denotes the following. Will denote the big set A if J is the empty set, or will be the intersection of all J in J of AJ, otherwise if J is not empty. And last time we saw an application of the principle of inclusion-exclusion determining the number of derangements in Sn. Today we'll do other applications. So let's start with some simple example. Let's say we have n and k natural numbers, and we want to count the following quantity. What is the number of functions f which are defined on some k set? Let's just call it a1 blah, 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 ak into a set with n elements, b1 all the way to bn, is so no restriction on the sets on the function, just count the total number of such functions. This is not too difficult, and it doesn't involve the principle of inclusion-exclusion. We look at f of a1. F of a1 can take n values, namely can be anything from b1 all the way to bn. Similarly, f of a2 can take n values and all the way to the end. F of ak can take n values, b1, bn. Therefore, the number of choices for our function is going to be n times n times n, k times, which is going to be n to the k such functions. So the answer for this first question is n to the power k. The second one. What if we want to count the number of such functions that are injective? So the number of injective functions from the set A1, AK to the set with n elements B1, Bn is question mark. So again, instead of guessing a formula, let's just try to figure out the answer and then write it down. The proof is similar to the one before. F of A1, if we start with A1, F of A1 can take n values, which are these ones, B1 to Bn. But now once we have chosen F of A1, F of A2 can now take n minus 1 values, namely it can be anything in the set B1, Bn, from which we throw away F of A1, because they cannot be equal since the function is injective. And similarly, F of A3 can take n minus 2 values, and so on, and F of AK can take n minus. Here the count is similar to the one that we did for k-ordered tuples. when we pick f of ak, we have already chosen values f of a1, f of a2, f of ak minus 1. So we have to subtract from the set of all n possible values, these k minus 1 values. So f of ak can take n minus k minus 1 values. Thus, you get this falling factorial n times n minus 1 times n minus k plus 1 injective functions. So now here's a question where the real reason for which I brought these problems in is, let's look at a number of surjective functions from our set with k elements, a1 up to ak, to the set b1 up to bn is question. All right, so let's try to figure out the answer first, and then we can write it down. And here, the argument cannot be similar to the previous two, because function being surjective, it can take repeated values, and it seems a little bit more complicated for each value b1, b2, bn to try to break down all these functions f according to how many times how many elements are in the preimage of b1 and so on, how many are in the preimage of bn. So here, what we'll use instead, we'll use the principle of inclusion-exclusion. And solving a problem with the principle of inclusion-exclusion is not difficult once you figure out what is your big set A and what are the bad sets A1, A2, AN. Here, the big set A is not too difficult. A is the set of functions from A1, AK to B1, Bn. And we know the cardinality of A from the first part. It's n to the k. Now we have to figure out the bad sets. So what are the bad sets? A1, A2, maybe AN or something. So here, a bad set of function will be a function that skips one value from the codomain, from the set B1, B2, Bn. So for j between 1 and n, let's define aj to be the set of functions f, again from our set a1, ak to our set b1, bn, with the property that the image of f does not contain bj. So bj does not belong to the image of f. So f of x, so this condition, bj is not in the image of f, is equivalent to f of a1, f of a, or f of a2, or any of them does not equal bj. Okay. So now with this notation in mind, it's not too hard to see that the set of surjective functions from the domain A1, AK to the codomain B1, Bn equals A minus the union of A1, A2, An. That's clear. And in order to evaluate this, to count the number of surjective functions, we have to determine the cardinality of this set. And here's in the first step, we apply the principle of inclusion-exclusion. And we get that this will equal, just write down the formula, summation over all subsets of indices of j minus 1 to the cardinality of j times a subscript j. And now we have to figure out what is a subscript j. So A subscript j is A if j is the empty set. So that's easy. What if j is not the empty set? Well, in that case, so A subscript j is the intersection over all j in j of aj. And by definition, this will be the set of all functions f with the property that the element bj does not belong to the image of f for every j in j. So for example, let's say a1 and 4, this would be consist of all the functions f such that b1 does not belong to the image of f and b4 does not belong to the image of f. Okay. So what's the cardinality of j? Well, from this expression, cardinality of j, aj, will equal the number of functions from the same domain, from a1, a2, ak, but now in the codomain, we're throwing away cardinality of j elements, namely those b's whose index come from the set j. So from the part 1 of this exercise, the cardinality of aj is going to be n minus cardinality of j everything to the power k, which agrees, if you see it, it agrees with the first formula here when j equals the empty set. So this is true for any j is a subset of n. Okay, and now with this formula, we go back and we plug it in here. And what do we get? We are going to get a summation over all j subsets of n of -1 cardinality of j. Now this a of j, you can replace it by n minus cardinality of j to the power k. And we can simplify this formula if we split the j's according to their cardinalities. So let me call the cardinality of j, I don't know, some number L, let's say. So this is going to be, so the sum will be a sum from L equals 0. How big can the set J be? It can be up to 1, 2, 3, all the way up to n. So L from 0 to n. How many J's of cardinality L we have? We have n, choose L of them. And then we pick up this part in the sum, the -1 to the power L times n minus L to the power k. And this is the formula for the number of surjective functions. So we'll put it here. This is going to be a summation over L 0 to n, and choose L -1 to the L, n minus L to the k. Yeah, it's perhaps not as nice as the previous ones. In one sense, you don't get an idea how large this sum is, because it's an alternating sum. So perhaps it's not so obvious where the power is. But nevertheless, it's a useful formula for the number of surjective functions from a set with k elements to a set in elements. We'll come back to this topic later on when we'll talk about Stirling numbers of first kind and second kind. Okay, so this is one combinatorial application of the principle of inclusion-exclusion. Let's go now to number theory, and let's talk about some famous function, Euler totient function, or phi function. So what is this function? So let n be a natural number and define phi of n as the number of all natural numbers a such that A is between 1 and n, and the GCD of A and n is 1. So phi of n is the number of natural numbers A that are at most n and are co-prime or relatively prime. Okay. You've seen this this function in probably your undergraduate courses. It appears in the Euler's theorem. Well, Euler's theorem is not quite a side name, but Euler's theorem in one of Euler's theorems in number theory, where if n is a natural number and a is an integer with GCD, which is co-prime with n, then a to the power phi of n is congruent to 1 mod n. This is this result in number theory, which is a generalization of another famous result, Fermat's little theorem, which states that if p is a prime and a is an integer, then, well, we can put it this way: with a is an integer with p, and p doesn't divide a, then a to the power p minus 1 is congruent to 1 mod p. So that's where one place where you'll see Euler's totient function. And it's not hard to show that Euler's theorem is a generalization of Fermat's little theorem. So let's come back to this function phi of n. Can we calculate it for any natural number? So let's start with some small values. Well, before we do that, let me give you a little bit of history. So the function was introduced by Euler around 1763. Apparently Gauss is the first one around 1800s to use the notation with phi. And another famous mathematician, Sylvester, used actually the name totient for it. And it comes from Latin, where tot means so many. So many numbers that are less than n and are co-prime with n. So that's a little bit of history. Let's calculate the function for some small values. So when n is 1, you get phi is 1, because 1 is co-prime with 1. When n is 2, you get the numbers 1, 2, and only 1 is co-prime with 2, so you get 1. When n is 3, 1 and 2 are co-prime with 3. When is 4, 1 and 3 are co-prime with 4. Then we get 5, and now we have a big growth because 1, 2, 3, 4 are co-prime with 5. And then the function at 6, 2, 3, 4, and 6 don't work, so 1 and 5, so that goes back to 2. And then at 7, it goes up again, you have 6 numbers. And at 8, you have all the odds that are going to be co-prime, 1, 3, 5, 7. And at 9, what are the numbers co-prime with 9? You have to skip 3, 6, and 9, so you take the rest, 1, 2, 4, 5, 7, 8, so you get 6. And at 10, you throw away the evens, and then you throw away, so you're left with 5 numbers, and then from the odds, you throw away 5, so you're left with 4. So this is the value of phi of n for small values of n. some things are clear. If P is prime, then phi of P equals P minus 1. And that's basically how Euler's theorem is a generalization of Fermat's little theorem. But how do you calculate the values of phi of n for other natural numbers? So we'll do that now. So if n is 1, then phi of 1 is 1. So that's pretty clear. So that's not a difficult. So let's start with let n be greater to be a natural number. And let's assume we have a factorization of n into prime. So you have the p1 to the e1, pk to ek be the prime factorization of n into distinct primes p1, p2, pk, where the exponents e1, e2, ek are natural numbers. So then phi of n has a very nice formula, is n times the product from I equals 1 to k of 1 minus p 1 over pi. So it's n times this product, and this product you see is less than 1 because you're multiplying a bunch of numbers that are all less than 1. So you'll get n times some fraction. So let's prove this result. And we'll use again principle of inclusion-exclusion. And as before, it's all a matter of figuring out the sets A and the sets, the bad sets A1, A2, A, whatever index may be. Now the set A, so what are we counting? So let's, if we look back at phi of n, its definition is that we're counting natural numbers A between 1 and n with some property. So the property is that the GCD of A and n is 1. So the first condition here kind of leads to defining the set A to be our set 1 to all the way up to n. And then we have to interpret this condition of GCD of A and n. So GCD of A and n is 1. That means that it's equivalent to the fact that no prime from the prime factorization of n can divide A. So P1 doesn't divide A, all the way PK doesn't divide A. So that's the equivalence between these two conditions. So that makes sense now to take as bad sets as A1 being all the elements A between 1 and n, such that P1 actually divides A, and go all the way to AK, all the sets A, with the property that, again, A is between 1 and n, and PK divides A. So let's figure out now, so well, with this notation in hand, what exactly is phi of n? Well, it's not too hard to see that phi of n will be the cardinality of A minus A1 union AK. And by principle of inclusion-exclusion, this will equal summation over all j subsets of the index set 1 to k of minus 1 to the cardinality of j times cardinality of A subscript j. So here we use principle of inclusion-exclusion. Okay. So let's calculate these AJs. As before, if J is the empty set, AJ is the set of our set A, which is the set 1 all the way up to n. Now, if J is not empty, then AJ is going to be the intersection over all J and J of AJ. And what is that? So this would be the set of all numbers between 1 and n, such that Pj divides A for every J in J. And here we'll use this important property that the primes are distinct, and this fact from number theory that an integer is divisible by distinct primes, even only if it's divisible by the product of their primes. So therefore, this set AJ can be written as all A between 1 and n, with the property that the product over all J in J of Bj divides A. Okay, so that's how it works. And if we plug this thing, this is AJ. Before we do anything, we have to deal with cardinality of AJ. And here on the top, cardinality of a empty set is n. Cardinality here of AJ is going to be the number of all A's which are divisible by this number here, which is a divisor of the number n, and so this will be n divided by that number. Okay. And now we plug it back into the inclusion-exclusion formula over here, and we will get that phi of n will equal the summation, and if we unpack that summation, you can get, I'll leave it as an exercise for you, you will get this very nice formula that we have here. Okay, so I'll leave it to you as a step here to figure out how to do this calculation and to get this formula for phi of n. Okay, now let's move on to another famous function, which is we'll see some connections between them in a second. This is called the Mobius function. And there is a Mobius function, a general Mobius function of a poset. So sometimes this is a Mobius function in number theory. So sometimes you'll see this called as the classical Mobius function. Okay, so how is this one defined? This is also a function defined on natural numbers. So it's denoted by mu with values integers, and is defined as follows. Mu of n equals 1 if n is 1, 0 if n is divisible by any square of a prime, if p squared divides n for some prime p. So whenever you have a square of a prime dividing n, the value of the Mobius function is 0. So that leaves the question, what are the leftover numbers? Those are product of distinct primes. So if n equals product of distinct primes of the form p1 product pk, and p1 pk are distinct primes, then the Mobius function is -1 to the power k. Okay, so let's do some examples to see how this Mobius function looks like. I mean, here we set 0, but it's actually, we set the set of integer, but this is -1, 0, and 1. So the Mobius function can take just these values. And so, let's see, we have 1, 2, 3. So mu of 1 is 1. Here, 2 is a product of 1 prime, so it's -1. 3 is a product of 1 prime, is -1. 4, there is a square of a prime in there, so it's a 0. 5 It's also just a prime, is -1. 6 is a product of 2 primes, 2 times 3, so we get a 1. 7 is a -1. 8 is a 0, 9 is a 0, and 10 is a 1. And so you have this sequence of ones, -1s, and zeros. Okay. So what's such a big deal about this function? Well, it's quite important and it connects to many things. So let's prove the following propositions. So let's prove two facts. One, let's say n is a natural number. Then if I sum up mu of d over all divisors of n, then I will get the following. I either get 1 when n is 1, or I get 0 when n is greater or equal to 2. Okay, so that's one fact. And second one, this is not, something similar for, it doesn't have Mobius function in it, but we'll see to it. The second is that if you sum up sum of d dividing n of the Euler totient function of phi of d, we will actually get n. And the third one is that phi of n, the Euler totient function, for which we just found the formula a bit earlier, can be expressed in terms of the Mobius function as the sum over all divisors of n, d, of mu d times n over d. So we'll prove some of these results now. Okay. So let's start with the first one. Well, when n equals 1, that's clear by the definition of mu of 1. So let's assume n is greater or equal to 2, and let's say n is p1 e1 pk ek, where e1 ek are greater or equal to 1, and p1 pk are distinct primes. Okay, now if we have a divisor of it, d, how will d look like? So if d divides n, that means that d looks like p1 f1 pk fk, with this f1 less than or equal to e1, fk less than or equal to ek. That's how it looks, the d looks like, the divisors. Okay. So as before, we have our n, p1, e1, pk, ek. These ek's are all greater or equal to 1. And we have our d, which is p1, f1, pk, fk. And here, maybe write it this way, f1 is between 0 and e1, and fk is between 0 and ek. Okay. Now, from the definition of the Mobius function, whenever we have one of these fj greater or equal to 2, that's going to give us that mu d is 0. Okay. So the only case that mu d will not be 0 is, so mu d won't be 0 when f1, fk are all in the set of zeros and ones. Okay. If all of them are 0, if f1, fk, if all of them are 0, then we have d equals 1, and so in that case mu of d is 1. But let's say if exactly r of f1, fk are, let's say, not 0, are 1, then mu d will equal -1 to the power r, because you have exactly r primes in distinct primes in the factorization of d. So now, how do we get our result? So we're looking for the summation over all d divides n of mu of d. Now, all the ones that have an f in them, fj in them that's greater or equal to 2, we can throw them away, because in that case, mu of d is going to be 0. So in this summation, the only ones that count are the f's that are all between 0 and 1. And if we have the situation that exactly r of them are 1, then in that case, the mu of d is going to equal minus 1 to the r. Well, how often does that happen? Well, to get r, how many ways can you have r elements from the set f1, f2, fk? How many ways can you choose them? Is k choose r. And what are the possible values of r? It's a summation from 0 all the way to k. And we get this alternating sum of k choose r minus 1 to the r. But here, from the binomial formula, binomial theorem, we can observe that this is just 1 minus 1 to the power k, which is 0. Okay, so that proves the first result here. Okay. Now, for the second one, what I want to prove is this important property of the Euler totient function, is that the summation over all d divides n of phi of d equals n. Okay. And this is not something that you may have thought about, but I guess if you, where is the formulas? Here. If you play a little bit with all the, let's do some example here. If I take my n to be 6, if I'm summing phi of d over all the, how does this work? Let me see here. Where's my term? Sum of phi of d over all d dividing n is going to give me n. So let's see here. So if n equals 6, what are the divisors of 6? They're going to be 1, 2, 3, and 6 itself. And the result states that if I sum up the entry 1 plus 1 plus 2 plus the 2 from here, I'm going to get the 6 that I started with. Okay. So that's this result applied to the situation that n equals 6. Okay. So how do we prove this result? Well, let's look at let's look again at the function at the set n. So we have our set n, which is a set of all the elements 1 to n. And initially, our function, totient function, counted those numbers from here, whose GCD with n is 1. But let's split these numbers from 1 to n according to what their GCD is going to be with the number n. Maybe the GCD of between those some of the numbers and n is not going to be 1. It could be something else. So this can be split in various, let's call these sets as D. Well, no, let's call it AD. These are the sets, let's say A between 1 and n, such that the GCD of A and n equals the number D. And we can do that. We can do this, this split in various ADs for every D that divides n. Okay, so in our situation, A1, it consists of all A's such that A, the GCD of them Let me change this A, it's not good notation because we used A before. Let's call it B, BD, B1. B1 will be all the ones that JCD of A and N is 1, and so on for all the other divisors of, you can have B2, B3, whatever, depending of the divisors of N. So how many elements do you have in each? So first of all, N, the set of numbers from 1 to N, is going to be a disjoint union of all these BDs. Because every natural number between 1 and N, the GCD between that number and N will be some natural number, and that natural number has to divide N. So that's the proof of this result. So this, I put a dot here because this is a disjoint union, and that implies that the cardinality on the set on the left, which is N, will equal the summation over all D in N of cardinality of BD. And now if you look at what we're trying to prove that N is a summation of phi of D for all D dividing N. This might give you an idea to what to do next, to how to get from here to here. So we'll try to figure out, we'll prove that B of D, the cardinality of B of D equals this phi of D. So here's how it works. So again, before, B of D is all A between 1 and N, such that GCD of A and N is D. Okay, so what does that mean? So that means that A looks like a D times A1, and N looks like a D times N1. Okay, that means the part of common being a common divisor. Common divisor means this part, that D divides both A and N. And the fact that it's the greatest common divisor means that the GCD of A1 and N1 has to be 1. Now, this is the same thing here as the GCD of A1, and what is N1? N1 from this equation is just N over D. Okay, so if we rewrite BD, it's counting A, but A is of the form D times A1. Now, over there we had A between 1 and N, and that becomes what in terms of A1? That is the same thing as A1 between 1 and N over D. And the fact that GCD of A and N is D, it becomes now this other condition here, GCD of A1 and N over D is 1. So this is the set BD, and if you want to calculate its cardinality, from here, let me put it this way. This is the same thing as the cardinality of all A1s. I mean, here it's D times A1s, but when we calculate the number of elements, the D won't matter. So the cardinality of BD is going to be the cardinality of all A1s that are between 1 and N over D, such that the GCD between A and N over D is 1. So that's the same thing as phi of N over D. So you have to be a bit careful. It's the cardinality of BD is not phi of D. It's the phi of N over D. So now how do we put it all together? We have N, it's a summation over all D, D divides N, of cardinality of BD, which is the sum over all D, D divides N, phi of N over D. But you can change, you can call E to be N over D, and as D goes over all divisors, E goes over all divisors. So this is going to be a summation over all E, E divides N, phi of E, which is the same thing to what I was trying to prove. Okay, the third one, the third part relating the Euler totient function and Mobius function, I won't prove it here. It will be you can prove it directly, but it will be a consequence of the next result, which looks very similar to, so this one to the principle of, it would be similar to principle of inclusion-exclusion. And actually, this classical Mobius inversion formula that I'll show you here, and the principle of inclusion and exclusion, they have a common generalization in the Mobius inversion formula for Mobius function for posets. And we'll talk about them later when we talk about chromatic polynomials in graph coloring in this course. For now, let me write down the classical Mobius inversion formula. Let f and g be two functions from natural numbers to real numbers. The following are equivalent. One is that for any natural number, let's say m, f of m is a sum over all divisors of m of d of g of d. This is equivalent with, for any n, a natural number, g of n is a sum over all d divides n, and here's a Mobius inversion, Mobius function appears mu of n over d times f of d, which is actually the same thing as the summation over all d divides n of mu of d. You just switch d and n over d, f of n over d. Okay. So these look quite intimidating at first. How in the world do you go from one to the other? So let's give one proof, one direction, and I'll leave the other ones. It's in the textbook, and I'll leave it as an exercise. So let's just go from left to right. Okay. So we assume one. So that happens for every natural number m. And now we want to prove part two. So we take, let n be a natural number. Instead of going at g on n directly, let's look at this sum. Summation of d divides n of mu of n over d f of d. So because we assume one, we have a formula for f of m for any natural number. So we have a formula for this f of d, which is here. And we use that. So summation d divides n mu of n over d. And now that changes to summation of e, let's say e divides d of g of e. So you have this double summation there. And the key to the this Mobius inversion is to switch the order, of summation. So when I have e divides d and d divides n, so I can switch this to summation of e divides n. And actually the g of e can come in front. And here I'm gonna have a sum over what? Well, it's gonna be over all d's. And now what happens is when e divides d and d divides n, it turns out that if you look at their n over d is going to divide n over e. Okay. And this is a sum of mu of n over d. Okay. And now from here, if I look at the sum of all e's, I peel off the e equals n here. So I'm going to get g of n. And plus, for all the others, in this other sum here, e is going to be strictly less than n. So n over e is going to be bigger than 1. And from the first property about the Mobius inversion, the Mobius function, the classical Mobius function, this summation will be 0. So we end up with gn. Okay. So I'll stop here with the classical Mobius inversion formula. Next time, I will describe the historical context in which Mobius introduced this function, and I'll describe some other remarkable properties of the Mobius classical Mobius function related to the Riemann zeta function. And from there on, we'll move on to other counting problems involving Stirling.